Hi, my name is Jiang. I'm a staff scientist at Oak Ridge National Laboratory. We are a U.S. Department of Energy Office of Science laboratory in the state of Tennessee. Today, I'm going to introduce to you our GPC Letters perspective article on electric double layer capacitors, also known as supercapacitors. A EDLC stores energy as double layers of electrolytes inside of porous electrodes, and it has much higher power density compared with lithium-ion batteries. It can charge and discharge in a matter of seconds. Due to their high power density, EDLCs have many applications, for example, in hybrid bus and hybrid electric cars. The motivation behind this work is to understand how the surface area, normalized capacitance, will change with the pore size for both the ionic liquid and organic electrolyte. The method we're going to use is called the classical density functional theory. It has the same mathematical foundation as the more familiar electronic density functional theory. But over here, we are talking about density of the ions and solvent molecules. So now we have an ion liquid confined in a slit pore, has positive charge on the surface. The question for us is, as we change the pore size, how the capacitance will change with it. What we are showing here is the surface area normalized capacitance versus the pore size as measured by the multiples of ion diameter. So when the pore size is about the ion diameter, we can see a sharp rise in capacitance, which agrees with previous experiment. And what we found new here is that as the pore size increases, the capacitance goes back up and oscillates multiple times until it levels off, and overall you have a decaying envelope. This capacitance oscillation with pore size is best understood by imagining that you have two walls far apart with each other as here. As the two walls move closer to each other, the electro double layers associated with the two walls will overlap and interfere, and the interference caused this oscillation. Next, let's move on to organic electrolyte, which is more widely used in both academic and commercial EDLC devices. The difference between an organic electrolyte with an ionic liquid electrolyte is that now you have neutral solvent polar molecules, and then you have cations and anions dissolving in it, and that's your electrolyte. And so in our classical DFT model, we take into account of the solvent molecule by using a dipole. Again, what we're showing here is a capacitance normalized by surface area versus the pore size. And the pore size is about 0.5 nanometer, which is the ion diameter here. You have sharp rise in the capacitance, which again agrees very well with previous experiment. And what we see here, as the pore size increase, now the capacitance go back up again. However, beyond the 2 times ion diameter, the capacitance is more or less flat with the pore size. This kind of invariance is due to that now the electro double layers is composed of counter ions packed together with the aligned dipoles, and also on the other side. And this kind of EDL structure is pretty much the same for this pore size, and this pore size. And that's why it gives you this invariance in capacitance. This interesting and exciting work was supported as a part of the first Energy Frontier Research Center and Oak Ridge National Laboratory, and in collaboration with Professor Jianzhong Wu of UC Riverside, who is expert on classical density functional theory. I think GPC Letters has become the crown jewel of the Journal of Physical Chemistry. It's my great honor to contribute a perspective article in GPC Letters, and thank you for watching this video.